Hello and welcome back to the channel. This video is going to be about chapter 2 of Salvadori's Structure in Architecture. This is a textbook that we are reviewing. And as you already know, there are 15 chapters. So this is the second one, and the name of that is Building Loads and Codes. So, as you already know, all structures must conform to a variety of regulations, and uh, those are building codes and zoning laws. So, some of these are regulated by local authorities, such as minimum setbacks, then minimum height and type of structure, and so on. On the other hand, safety related concerns, load carrying capacity, the strength of materials used, and fire resistance of materials are governed by the International Building Code or IBC. So, and it was published in the year of 2000 by ICC, that is the International Code Council. And that actually replaced the three previous codes used in the different regions of the country. So the determination of the loads acting on the structure is a complex problem. The nature of loads varies with the design and the location of the structure, and also the materials used. So loading conditions may vary with time, change of occupancy, and applied loads. And those are some of the natural forces as well. So the most important loads on an architectural structure change slowly with time. They are called static. These include the weight of the building, furniture, and so on, thermal expansion and contraction, snow, as well as lateral earth and water pressure below grade. So, rapidly applied loads such as violent winds, earthquakes, reciprocating machines, and explosions are considered to be dynamic loads. So, the IBC divides loads into various classifications such as dead, live, wind, snow, seismic loads, soil and water pressure, and so on. So the load to be carried by the floor of a building varies so much depending on the occupant of the floor, and the distribution of furniture, weight of machines, or the storage of goods. So the equivalent load is derived on the basis of structural evidence for such type of building and is modified from time to time as new conditions or knowledge arise. So code loads are conventional loads. A floor load may be assumed to be a constant number of pounds on each square foot or per square foot, even though in practice no floor is ever loaded uniformly. So, whenever the loads on a building are not considered by codes and when they present characteristics that may endanger a structure's life, they must be accurately determined through experiments or by mathematical calculation. The effect of hurricane winds on a skyscraper may have to be found by means of aerodynamics tests on a model conducted in a wind tunnel. And it's not always sufficient for the designer to consider only code loads, since the responsibility for the strength of the design rests with him or her and not with the code authorities. This is particularly true in circumstances where code regulations do not apply. So it is therefore essential for the architect to acquire an awareness of loads. So let's talk about dead loads now. So to determine the required structural strength, the loads to be applied to the components are dictated by the IBC. because the loads carried by the floor of a building vary depending on the occupants of the structure, location of furniture, the storage of goods, and so on. The code substitutes an equivalent load under which the floor will not fail or deflect so much as to become unusable. So this code load must therefore be a multiple of the load that would produce failure or unacceptable deflection. This multiple is denoted as the safety factor or SF. The SF accounts for uncertainties in load estimation as well as irregularities in materials and workmanship. So new techniques based on probability methods have been developed that compare the statistical variations of loads and of the structural strength of the materials used in order to determine an optimal safety factor or SF. So a further discussion of these techniques will follow the section on live load. So that's in the next subsection. And a more detailed analysis of load and resistance factor design, or LRFD, is actually beyond the scope of this book. That's kind of like the advanced structures. So let's talk about live loads. Live loads are characterized by their transient nature. It is likely obvious to the reader that people and easily movable furnishings like chairs are live loads. But um, so two are even more stationary furniture and shelving that is rearranged less frequently, but which is otherwise not permanently attached to or supported by a floor or wall. So the unavoidable weight of the structure itself and the weight of all loads permanently on it constitute its dead load. So we have already determined that. It is one of the paradoxes of structural design that one must know the dead load beforehand in order to design the structure, while it simultaneously cannot be determined until the structure is designed. So it's all based on the um, educated guess. So the dimensions of a structural element depend essentially on the loads acting on it. And one of these loads is the dead load, which in turn depends on the dimensions of the element. So in many cases, the dead load is the most important load on the structure. It may greatly outweigh the other loads, particularly in large structures and those built of heavy materials, for example, in bridges, roofs, and other structures. So, in certain cases, the dead load is not only important but also useful or even essential, as, for example, in a gravity dam, where it is used to resist the horizontal pressure of water. And again, please refer back to the textbook. There are a lot of images and sections and graphics. So there is a nice chart here as well, and that's the weights of some building materials. So for example, aluminum is 170 pounds per cubic foot. Steel is 490 and sand is 95. So that gives you like a little breakdown of these materials. So let's move to live snow and wind loads. And that is very important to actually take into considerations when the building is designed. So loads such as the weight of people, machines, movable furniture, partitions, non-structural elements, and movable fixtures are of an uncertain nature and of uncertain location in the structure and hence require safe averages established by the codes. So, for example, when you look at the occupancy loads, and again, there is a little chart for that, you can see that the balcony is 80 pounds per square foot. Then the library is 150 pounds per square foot. So you know that books are very heavy. And at the same time, the theater is 60 pounds per square foot. So that is something to remember when you design the building. So also, let's take a look at the snow loads. So the weight of snow depends on the climate and elevation of the region where the building is to be erected. So, for example, according to the IBC, it is equivalent to 30 pounds per square foot in New York, whereas it is 50 pounds per square foot in Minneapolis, Minnesota. So, and there is a map showing snow loads on flat surfaces in the continental United States. So please refer to that. Um, it is published online, so that can be easily retrieved from the website. So, snow load is usually measured on the horizontal projection of the roof. So, and the slope of the roof affects the retention of snow. A steep roof has lesser retention than a flat one. And also, there is a picture of the high school gymnasium that failed under the snow load, and that was in Blacksburg, Virginia. So the whole structure collapsed because the snow load was not properly calculated. Let's talk about wind load. So, wind loads can be quite substantial in coastal and island areas subjected to hurricane speed winds. So, in recent years, the IBC has increased the maximum design wind velocities in these regions to better safeguard life and property from devastating storms. And again, there is a map where you can see maximum wind velocities in the United States. And for the most part, it's southeast, it's Florida, Georgia, North Carolina, and so on. So that is formed in the ocean and that comes to the coast. So um, you see that these areas are referred to as special wind regions in the IBC, and the vast majority of the interior of the continental United States is designed for a wind speed of 90 miles per hour. Um, also there are different bracing systems, and let's take a look of them. So horizontal wind bracing system. For example, in Akashi-Kaikyo Bridge in Japan, diagonal chevron bracing is used in the horizontal plane to stiffen the structure for transfer of the lateral wind forces to the supporting piers. The bracing creates a horizontal truss that functions as a very deep beam spanning horizontally between the supporting piers to resist wind forces. Let's take a look at the picture. And also there are schematic diagrams showing the chevron bracing, cross bracing, and knee bracing. And that is the vertical wind bracing systems. So, and each of those serve the function of preventing the structure from displacing laterally under the horizontal loads of wind or seismic forces. So members that serve to resist compression as well as tension must be noticeably heavier than those that can be sized for tension. So also what we need to remember here is bracing is only one plane is shown here for clarity, like in these particular diagrams. But when we look at the buildings, they must be constructed with bracing in multiple directions. So please do not take this as the direction to use those images, but please always design to the most stringent requirement and just design so the bracing goes on um, the core of the buildings as well as around the perimeter. So it should be recognized that the depth of snow and wind velocity have statistical variations. So wind may be calm one day and become a gale or a tornado on the next day. And there may be no snowfall and a major snow blizzard the next day. So such extremes of weather are infrequent, and designing structures to withstand them with the same factors of safety as required for more frequently occurring loads may be prohibitively expensive. So, in the strength of structures is also statistically variable. The strength of concrete, for example, depends on the size and the strength of the stones in it, and the amount of water, and also the length of the cure time. So, to account for these variations of loads and strength, a stress strength interference method may be used. So, loads are converted into stresses, and their frequencies of occurrence are plotted together with the frequencies of structural strength. So, here you can see an example of a staggered truss framing system. So that goes that actually connects the concrete floor slabs. So again, there is an example. There are beautiful images such as the Fiat Tower in Paris. You can see the structure and you can also see the stress strength interference. There is a diagram and there is a frequency going to the y-axis and stress going on the x-axis. And then the intersection of the mean stress and mean strength is the probability of failure. And you can actually play with that and just make sure that the diagram can be improved, and you can definitely reduce the stress if you move a stress diagram to one side and a stress diagram to the other side. So let's take a look at the thermal and settlement loads. So that is another thing that we need to remember. So as we know that all structures are exposed to temperature changes and change shape and dimensions during the cycle of the day and night temperatures. So if restrained against movement, the effects of changes in dimensions due to thermal expansion and contraction are often equivalent to large loads, which may be particularly dangerous because they are invisible. Um, so, for example, and there are actually a few examples of that, and you can see that sometimes the structures are supported on a roller or rocker bearing, and you can see that there is a bridge in New York that is supported like that. So there are a few different variations on how to do that, and also there are a few graphics showing how the dome um, expand and contract. So those thermal movements are shown in position with increased temperature is expanded, it's the expanded dome, and with the decreased temperature, the contracted dome. So, and that varies every single day. So also, you need to account for the asymmetric thermal distortion of a dome if the sun's heat come from one side. So, and that is something that you need to actually consider when you do the calculations. So, for example, there is another condition producing effects equivalent to those of high loads, and that may be different from the uneven settlements of the building's foundation. So a soil of uneven resistance loaded by the weight of a building may subside more in a specific portion of the foundation than in others. And the soil deflections reduce the support of the foundation in certain areas, and the structure may tilt. So, and of course, everybody knows such an example as the Leaning Tower of Pisa in Italy. So people love to take pictures of that, like they're holding that tower from falling down. So, but actually, the that happened because of the foundation settlement, and it was finally stabilized back in 2001. So also there are different types of uneven settlements of foundations. So uneven support settlements causing either a shearing of a portion of the building or deformation of a frame. And here you can see graphics representing that. Also, there is a locked in stress, and you can see that that it's locked in a steel beam, and that is due to the rolling manufacturing process that may be released if the beam is cut down at the center of its length, resulting in an outward curling of the sections. So that sometimes may happen as well. So please remember that there could be some deformation of the materials due to thermal and settlement stresses. And we are moving to the dynamic loads, and that is the last section of our chapter 2. So all the loads considered in the preceding sections were assumed to be stationary or um, slowly with time, and they are considered to act statically. In codes, even the wind is assumed to act statically for low and moderate height buildings, although it obviously does not. So, in earlier times, in order to ring a heavy bell, a church keeper would pull its rope rhythmically, and the bell would swing progressively further until eventually it rang. So, and a similar but more common experience is that of being pushed on a swing. So, if one pushes the swing, then the inertia is difficult to overcome. So, and then it basically comes back. So, and that being pushed on a swing is a form of resonance. A person will sway with a natural period of vibration that is related to the length of cable or rope on the swing. So, physics dictates that weight does not affect the period of vibration. However, the greater a person's weight, the more inertial resistance must be overcome. A single sharp push may require significant force to overcome inertia. By pushing in synchronization with the period of vibration, though, only a very small amount of effort can have a large effect, over time sending a person higher and higher on the swing. So, and the dynamic loads are exerted on structures in a variety of ways. So high velocity winds may be similar to a hammer blow, and a company of soldiers marching in step exerts a resonant load on a bridge when their step is in rhythm with the oscillations of the bridge. So, and here is another image of the Brooklyn Bridge under construction. So, and there is a sign saying that it's only safe for 25 men at one time, and do not walk close together, do not run, jump, or trot, break step. So that is something that is important when you construct the bridges. And again, there is an image of the London Millennium Footbridge. So it was built in the year of 2000, and it actually had to be closed down, and they had to install the fluid damping mechanism in order for it to withstand the pedestrian load. So, um, in a variety of practical cases, the dynamic effects of a load are 100% larger than its static effect. So, most loads applied to architectural structures do not have impact characteristics, except those due to hurricanes, tornadoes, and earthquakes. Because such extreme winds have dynamic characteristics, the pressure predicted from the wind velocity formula may be doubled. And you can see another diagram showing the dynamic loads. So when we look at the earthquakes, an earthquake is a sudden motion of the ground. So the series of randomly variable jerks transmitted to a building through its foundations produces much larger oscillatory motions of the higher building floors. So an earthquake occurs when the locked-in stresses in the earth crust generated by movements in the molten mantle of the earth become high enough to suddenly shift a portion of the crust with respect to an adjoining portion, opening up at times gaps several feet wide and hundreds of miles long. So, and over underground fractures called faults. So, in the state of California, earthquakes occur frequently, and when architects get licensed before they actually can obtain a license in the state of California, they need to pass the architectural registration exams plus the California supplemental examination that will actually provide them with the knowledge of how to design for the earthquakes and the dynamic loads. So, the study of earthquakes and the design of earthquake-resistant structures is still a relatively new science. Just as circularly expanding waves are generated by a stone dropped in a lake, the explosion of a small charge embedded in the earth crust generates outward moving stress waves, which speed depends on the value of the stresses locked in the crust. So this is there is more science behind that, and if you are interested, please refer to the California structural systems or Japanese ones, because in Japan there are also frequent earthquakes. And you can see the seismic zone map of the US. So that is available online at the US GS website. So you can always go back and check. So, and we are moving to the other section, seismic base isolation. So how that works. So base isolation is an effective and increasingly popular strategy to reduce the impact of seismic forces on structures. Base isolation separates the building or bridge structure from the ground motion with deformable foundation structures. So, and there are a number of variations on how to do that. So please refer to the pictures. You can see that, or you can actually Google that, or you can go to the YouTube and you will see multiple videos, including um, just a person standing on the roller skates on the table, and then the table is moved under that person. The person is still stable just because the those wheels are moving back and forth, and the person is actually not. So, and you can see there is another image of the feedback dynamic damper, how that works. So they are calibrated to match the building's natural period of vibration. So, and the dampers may be actively controlled by a computer mechanism or passively act by gravity or a combination of both. So there is another system of semi-active tuned mass damper, and that's in that John Hancock Tower in Boston, Massachusetts. So that actually the damper helped to counter the sway due to wind load. So this is a complex system that is installed there in the building. So resonant loads occur at times in architectural structures for other reasons as well. A piece of heavy machinery may vibrate because of the motion of its parts. If this vibration has a period equal to that of the supporting structure, the vibrations of the machine will be transmitted to the structure, which will swing with increasing oscillations. Floors, foundations, the entire building may actually be endangered by these small loads. So another thing to remember here is the passive tune mass damper, and you can see that there is a picture of that Taipei 101 passive tune mass damper. So that is the suspended sphere that has the same fundamental period of the building itself, and it actually it counters the sway by its own inertia. So it's an interesting concept as well, and I would like you to go back to the textbook and actually take a look at how that works. So, and this wraps up our chapter 2. Thank you so much for watching. I will see you in chapter 3.